Okay, if 5.93 grams of aluminum bromide is dissolved in 250 grams of water, what will the freezing point be? We need to have the molality. So for number one, we've got two equations we're working with here. This is the freezing point, temperature of freezing, equals I, Van Hoff factor, freezing point constant, and molality. And then once we find the change in freezing temperature, then we take that change in temperature of freezing and put it into this equation, temperature of final minus temperature initial. Okay, so we have to find I and M. We do look this one up. To find M, well, I'll tell you what, let's do I first because I need to find a balance formula anyway. So we've got aluminum bromide. That means we have an aluminum and we have bromine. That's that's a metal and a non-metal. So this must be an ionic compound, which means that these are charged particles. So this has a 3+ charge and this has a 1 negative charge. And to get that to be balanced, we need 3 bromines. So our formula is going to be AlBr3. And because we have 1 aluminum particle and 3 bromine particles, if this is a soluble salt, I is going to be 4. Let's see, for the molality, then we're going to start by putting the amount of solute in the problem on top of a fraction, 5.93 grams of aluminum bromide on top of the fraction. And we're going to put the amount in the problem of the solvent, 250.0 grams of water. And then we want to convert that into those terms or those measurement units that fit the molality concentration unit. So the solute has to be turned into moles, the solvent has to be turned into kilograms. To get this into moles, I've got to have the molar mass of this. So let's see, I've got aluminum and bromine. So I need the atomic masses of those. Atomic mass of aluminum, 26.981538. Bromine, 79.904. And there's 1 of these and 3 of these. So now we need to add these two numbers together. $693.538. The last 3 digits are the result of adding to an empty slot here, so those last 3 digits get rounded off. And so we have 266.693. I'm sorry, that's a 4 here. You're right. Grams of aluminum bromide equals 1 mole of aluminum bromide. Okay, so now from this equality statement, we can build a conversion unit here. We want to match the units and species on the top here with what we put on the bottom, and that's this side of the equality statement. 266.694 grams of aluminum bromide. And the other side of the equality statement goes on the top. And that allows us to cancel units and species in the same way we cancel x's and y's in algebra. So we've got our solute now in moles. Now we want to try to convert the solvent amount from grams into kilograms, because that's the way that molality, the concentration unit molality, is set up. For that, we need an equality statement where we have 1,000 grams equals 1 kilogram. And we can do the same sort of thing. We got grams on the bottom this time. We want grams on the top here to be able to cancel it. And the kilogram goes in the bottom. And that allows us to cancel the units of grams. So we have kilograms of water. That's what we want on the bottom anyway. So now we're ready to do the math. So let's see. 5.93 times 1,000. Enter. Divide by this number. Divided by 250.0. Then divided by this number. Divided by 266.694. Enter. And we get 0.088940. 883,559. You may have fewer digits, but that's fine. That's just the way your calculator works. We're going to round it off anyway. We look at the measured or calculated numbers in the problem. This number is measured. It has 3 digits. This number is measured. It has 4. This is calculated. It has 6. And these other numbers we don't use when we're figuring out significant digits. We want the one with the least digits. That's this one. And our final answer needs to have the same number of digits. Leading zeros are not significant, so here's our first significant digit, 1, 2, 3, and round off from there. We want to keep our units and species here. We've got moles of aluminum bromide on the top of this fraction, across the top here. We have kilograms of water on the bottom. Okay, let's round off then. 0.0889, and since moles of the solute per kilograms of water or the solvent is molality, we can simply shorthand that by writing the lowercase letter m for molality. We need to describe what the solution is, though. Since water is the solvent, we can simply say aluminum bromide or aluminum bromide solution. Okay, and that's the molality. That's the part we're going to plug into this part of the formula. So we now know that I is 4, and this is this number here. K sub F we're going to look up in your textbook. You have a table in there for list the freezing point constant for water. So we're ready to plug those numbers in. So we got change of temperature and freezing equals I, which we said is 4. The K sub B, K sub F. K sub F for water is negative 1.86. Units of measurement are always going to be listed in the column labels, okay, in a table. So we include the units of measurement from the column label, degrees C per mole. And now we're ready to multiply by M, which is this number here, 0.0889 molar. And just to keep everything arranged nicely so that we can do cancellations, we're going to put everything in fraction form and cancel molality the same way you cancel x's and y's. So we're ready to do the math here. So we've got 4 times negative 1.86 times 0.0889, and I get negative 0.661416. This is a calculated number. This is a calculated number. This is a counted number. We're not going to use this number for figuring out significant digits, only these other two. And the one with the least digits is this one, so we're going to round off to 3 digits. We have units left of degrees C. And we're going to round this to 0.661 degrees C. And that's the change in temperature. Negative. Right, it is negative. That's the change in temperature. So we're going to plug that then into this equation, where delta T, the change in temperature, is equal to the final temperature, that's what we're looking for here, minus the initial temperature. So delta T we have is that number right there, negative 0.661 degrees C. And temperature final we want to find. Temperature initial is in this case, the freezing temperature, because that's the initial temperature we're looking for, of the pure solvent. The pure solvent here is water, and the freezing temperature of water is 0.00 degrees C. So now we're going to add this number to both sides, plus 0.00 degrees C. So this basically cancels out here. And we've got the temperature final is going to be negative 0.661 degrees C. Since I don't have a digit in that slot right there, really it's probably better if we rounded off that last digit. And we get negative 0.66 degrees C equals T. So that for our temperature final. Okay? That's problem number 1.